My name is Mark Davis. I'm with Kitenga. We're a Santa Clara, California startup, and we're working closely with Lucid Imagination in terms of building analytic products that work over big data on top of both Solr, Lucene, as well as over Hadoop and other big data technologies. And so today, what I'm planning to do is to show both how to create analytical pipelines that work over Hadoop, but also how to use those analytical pipelines to produce metadata and other types of data out of unstructured information that can then become searchable, and then how to bind search experiences to that. And the title of my talk got kind of confused a little in the program. It's special English, as they say in Voice of America, but this is probably a better title, Enabling Big Data Search via the Lucid REST API. And so our goal is to combine these kinds of big data technologies together with search technologies. And one of the things that we've found to be very useful in terms of being able to do that is some of the enabling infrastructure that Lucid Imagination is providing on top of Solr in order to support that. And I just got a preview about an hour ago of the Lucid announcement tomorrow about big data. And so there's some more excitement coming. So we're all familiar with the story, and you've seen it here within this venue, that big data means many things to many different people. Enormous transactional data for some people, enormous semi-structured or unstructured information, depending on where you divide the lines on those sorts of things, semi-structured being like log file analysis, and unstructured being text typically. In some way it's too big for databases, or the database technologies are not suitable for it, and new tools are needed to do it. And that kind of big data problem has been broken down in different ways. One way is to talk about volume. Obviously it's big, so you have the dimensionality associated with that. But also velocity, how fast is the data moving through your system? I wasn't able to see the Zeus talk earlier, the last one, but I'm sure they have a velocity problem in addition to a volume problem. But then finally, variety, and that is where the data takes on multidimensionality, where you're trying to create new metadata out of it in order to enable new ways of interacting with the data. And all of these different dimensions are areas where we're trying to make an impact. With the possible exception of velocity, we're still waiting on real-time capabilities, and Hadoop is a batch process and things like that. So part of our challenge is on the indexing side. And in terms of the challenge there, how do you gather up resources to be able to index them? That can be a very simple task in some cases if the data is locally available, but it can also be very complex. You have a lot of data cleansing problems in terms of organizing your indexing pipelines and to be able to manage the different types of formats. When this becomes a big data problem, that problem is amplified even more, because in many cases, the ability to unpack a PDF file or to unpack a Word docx file is the dominant amount of time for processing the document. It's not the indexing time, but it's simply the cracking of the format and the extraction of the data. Also, the time to get at the remote resources may be a dominant factor in terms of your ability to gather resources. And so that can form a very significant bottleneck in terms of being able to make use of external and internal big data resources. A second area of where it becomes problematical is in terms of the ability to extract metadata. Now that may be prepared metadata on the one hand that pre-exist on these documents, whether it's the author of the document or Dublin core metadata and things of that nature. But our technology is specifically designed and comes out of the box with the capability of doing other things that take this sort of up another level. And that is the ability to extract named entities automatically from text. We have multiple different ways of doing that to extract people, places, organizations, in the biological domain to extract protein names, DNA sequence names, cell line identifiers, and things like that. We just maybe show you a real-time demo where this was just in the news, of course. You can look at some extracted biological entity data, and you can see that's about mad cow disease, for instance. The ability to apply machine learning, both in terms of supporting that capability for creating new metadata and extracting metadata to do the disambiguation task associated with entity extraction, but also in terms of broader categorical data about that data. What is this document about? What is its class within a taxonomy or an ontology related to the business? And then ultimately to be able to do semantic analysis. What are the relations that are expressed within the data? What is IBM acquiring this week? Things of that nature that reflect somehow interactions or relationships expressed within it. Finally, an additional bottleneck in terms of being able to make use of unstructured information within a big data framework is schema management. The ability to map all of this new metadata that's been created into an appropriate schema in such a manner that you can effectively bind analytic tools on top of that data. You know, on the one hand, one search model is that you just pour it all into a big index. It is essentially flattened, and then you can search over any of it. But you're not going to be able to answer questions like, when I find all the documents that contain the word Japan, what are all of the organizations that are present within those documents? This is the realm of faceted search, and this is where schema definition and collection management becomes important. And collection management as an add-on to that in terms of creating new collections, being able to manage them, migrate them, and things of that nature. So these are all indexing challenges that relate to big data. And then big data also, and small data for that matter, has search experience challenges. How do you create the end user search experience that really makes use of all of the varied types of metadata as well as the index itself to be able to do different tasks? That is, with your initial query, as it turns out, people can form queries based on their SAT verbal scores, or directly proportional to it. In other words, your verbal fluency as a user of a search system is directly related to your ability to form new queries and to form initial queries, the quality of the responses that you get. In other words, you're guessing about how to reformulate your query. Over time, as we use search systems, we start to develop intuitions about them. But we want to provide somehow within the framework of the end user search experience, the ability to overcome those limitations, to provide guidance associated with how to form search queries, how to refine them, and if you can't really guess the right word, well, maybe at least you can see it if it's presented on a page as an alternative to be able to get at it. And that helps you to refine the query through faceted guidance. And also, we want to be able to combine analytic tools directly within the search experience so that we can start to answer questions visually about the entire corpus of text and the entire corpus of semi-structured information that may have been generated out of your indexing process. Finally, how does the end user evaluate the relevance of a given document? Well, you know, the Google experience and what we're all used to, you just read all the documents and you try to find the one that's relevant to you. And you may go back and refine your query in order to do it with the limitations that I just mentioned. So, and part of that, you may read the keyword in context, the KWIC or quick. You may read the metadata associated with it. And you may also just ultimately read the document because you're scared about missing a piece of information. So can tools with all of this metadata that's being generated be created that enables or accelerates the process for the user to ultimately be able to determine the relevance of a given document? And so I'll show you a little bit about that today as well. And so in terms of our solution to these kinds of challenges, they take on two different forms. First off, we want to enable fast metadata generation. We want to overcome that indexing bottleneck that comes about partially due to indexing speeds, partially due to the cost associated with being able to do things like natural language processing and machine learning, partially due to the difficulty associated with acquiring the data, and partially due to the difficulty or the time associated with extracting the data from its native format. And to do that, our solution builds out on top of Hadoop, and so we parallelize it. Many of you probably remember the days of Corba and maybe Beowulf and MPI, and there was this very complex zoo associated with being able to do distributed processing. And it was extremely complex, and if any of you remember Corba, it went to mind-numbingly complex at the outside. So with Hadoop, where for highly parallelizable problems, as most of you probably know, we get a standardized capability for being able to distribute, and we get guarantees associated with their access of the different individual nodes to the different parts of the data to be able to ensure data locality with respect to the processing and so forth. With Mahout, we get scalable machine learning capabilities as well. Still in development, still slightly embryonic, but some interesting and good work going on there to support that. And one thing that we do in particular that's related to our customers in the US intelligence community is that we've implemented GPU clouds under the covers within the Hadoop framework itself. So where you have numerically intensive problems for generating metadata, for example, machine learning using support vector machines, things of that nature, you can spin those off into the GPU cloud to be able to accelerate the value of there. Have to be a little careful with data marshaling and things like that, but it enables that. And so the first aspect of this in terms of solving the problem is just to be able to do it more quickly through distributing the process and throwing additional technologies and tools at the problem. But the other problem in terms of managing and controlling collections and schema and how big data interacts with that, as we generate all this metadata out, how does it get into the index? That's where we turn to the LucidWorks Enterprise API ecosystem to be able to support us. We found that it provided through RESTful API and relative orthogonality a added value on top of Solr in its native form. So I'd like to just wax poetic for a few minutes about why we want to do this sort of thing. Oftentimes the people who focus on transactional data within an organization simply talk about databases, and databases are not suitable for text. Anybody who's used the Oracle text plugin, I shouldn't badmouth anybody, but would suggest that might be true. There are some great limitations associated with this sort of thing. How do we get across that chasm from the unstructured information into structured form? And so one way of doing it is through extracting different types of metadata. And this metadata may be people, places, organizations. You can also see here down the right-hand side that we have much lower level information like sentence breaks and splits and stop words. But then we have also negative sentiment and negative sentiment leading words and terminology that's associated with sentiment, usually just initially at the lowest level, just collections of adjectives in English that, you know, perform poorly and things like that, bad product. And then we also have things like the product sold and product launched. And so you can get additional information. It's usually very domain specific. If you're familiar with natural language processing, there's a lot of knowledge engineering that goes into the process to attack any given vertical. So this shows this capability. I'll show you the biological work in a few minutes. But it can be rapidly changed to meet the particular domain needs as well. So for example, if you're going after products in electronics and you want to get all the product mentions off of a website, you can import an electronics products catalog and be able to make use of that information fairly quickly. The types of capabilities that are involved in doing this sort of extraction task typically start with tokenization, which is the segmentation of the text into words. Sometimes that's more complicated than others in other languages that are not white space separated. And I can tell you some funny stories about that. Lemmatization, finding the root form associated with a word. Things like parts of speech tagging, which often uses a machine learning combined with rules approach to be able to do that. And then you have your choice at that level, kind of. There's several different ways of doing it. One common way is to use rule systems on top of that, and these are called cascaded finite state transducers. They take the patterns that you observe, like capitalized word, comma, ink in English, and they say, even if I've never seen that before, I'm going to guess that that's a company name. And so those sorts of rules sort of build up over time. And the net effect of that, going back to our core theme here, is that they slow down the process. And so you start to, the more and more the depth that you want to add in terms of those layers, now after company names and so forth, I want to find relationships between them. That's another layer on top of it. All of that slows down the process and suggests the need for this kind of parallelization. The other nice thing in terms of parallelization is that the knowledge contained in one document doesn't necessarily affect the knowledge contained in another document. So it's generally highly parallelizable. There are some exceptions to that, cross-document summarization and things like that. But the alternative to doing that is to use machine learning-based approaches, and actually hybrid approaches are often the best all around. And with machine learning, you don't assume that you can create those patterns. You assume that somebody can identify them and maybe mark them up, and therefore a machine learning algorithm can then infer those patterns and apply them in those inferred relationships additionally. But that creates a new knowledge acquisition bottleneck that you have to have somebody go through and mark up all these documents. If you have pre-marked up documents, that's useful. You can sort of bootstrap a little bit and learn from it. But it's not a silver bullet either. So oftentimes we combine these so that you have finite state methods, and then on top of that you may use machine learning to help do better guessing and improve the what's called the recall associated with these different tasks. So once you've got this kind of metadata, then the question is, what do you do with it? Well, you want to index it, but then you need a query language that really supports the ability to traverse over that data, to support all of these different capabilities on top of that. Faceted charting, faceted browsing, resource integration ultimately at the top, spell check, auto-suggest, and many, many more. So, Solr forms the perfect solution for us in terms of being able to get at that data once we index it. We can also look at the metadata that's been extracted separate from that, just looking at it directly on Hadoop. But that's one of the kind of integration stack that I'm going to talk about here today. And I just want to just run through really quickly a few use cases. And our goal is to go to a proof of concept in about a week. These are all so-called open source intelligence problems that exist out there. And since we also work with the intelligence community, we try to always do these things over data that's freely available and so forth to show it. Here's competitive intelligence. Your sources here are your competitors' websites, their patent portfolios, their documents, and so forth. And we want to be able to extract relationships and metadata from it, and ultimately to create a search experience. And I'm going to zip through these pretty quickly because I'm running a little behind. So what is our goal? To understand the IP among various competitors, to assist legal teams with litigation if they need to litigate, to create a custom search experience to enable the discovery of all this. And so, for example, with this POC that I'm talking about right here, we had custom metadata extractors, custom entity extractors that focused on electronic parts, different types of memory devices, flash memory, and things of that nature. And here's an example of how quickly your data problem can scale. Let's say that I'm an electronics manufacturer and I want to start crawling my my competitor sites. There's a lot of PDF out there, and there's a lot of videos and so forth, but this sort of gives you an idea. And this starts to get into biggish data, and can take that kind of scale, can take on a single machine to be able to do document extraction, to be able to do information extraction, then or entity extraction, to be able to do the indexing task. The indexing task becomes a very small part of that overall pipeline, can take days to be able to do this. Here's an additional use case, drug discovery, and the goal is to work over different publicly available abstracts and information, and to be able to extract from the English version of those documents relationships, pathway information, and so forth to create a faceted search experience that's customized to the particular domain. And so with the FDA, for example, we worked on yeah, I shouldn't badmouth. I was a Microsoft employee, so I have to avoid these things sometimes. But yeah, FDA currently uses Google Search Appliance. It could be better. Internal regulators can't find accession numbers for drugs that are in the regulatory pipeline because they just didn't index the so-called NDA numbers or regulatory number associated with it. And so we created custom extractors for those accession numbers, ontology of active ingredients for the drugs. Now, this sort of case, not very ambiguous, so very easy to import hydrocortisone into the thing because it's not going to be confused by the natural language extractors. Media intelligence, this is slightly interesting from the second talk today. We also indexed Wikipedia, and we cross-correlated it with IMDb. And this was very, very tricky and required a lot of custom work, because IMDb dumps are in a custom database dump format, and Wikipedia, as was discussed in the second thing today, is filled with all kinds of strange markup that's necessary for rendering it, but not necessary for indexing the content. So what I'd like to show you now here is, well, I want to talk a little bit more about the indexing pipeline. We put our crawlers on Hadoop. We do document format cracking on Hadoop. We do extraction, information extraction on Hadoop and filtering. And then we forward via HTTP to a separate cluster that lives separately from the Hadoop cluster and is sharded the documents. Intermediary files through this whole pipeline then remain on HDFS, the Hadoop distributed file system. So if you need to go back and tweak something intermediate scale, you can do so and still be able to carry on without needing to recrawl and everything. And so what we found was there was a missing piece to this puzzle, and that is how do you map the schema that's going into the search engine. So if you're creating a new piece of metadata, say drug name, extracted from FDA data directly from the website, you need to either go in and modify, as you know, the schema.xml and Solr config.xml, and then you need to look at the errors that are being generated by the Solr cluster or the Solr engine, and you need to say, oh yeah, I guess I didn't assign that particular piece of metadata correctly I forgot that I needed to make it multi-valued, for example. And what we do is through the LucidWorks Enterprise API, we have the ability to control all that at the front end directly from our big data technology. So it addresses the impedance mismatch for getting your data indexed. And so I'll just show you a demo of that. That's in case the demo isn't available, slide. So slight screen real estate issue here, but this is our Hadoop controller. You create workflow pipelines by dragging and dropping components onto a stage and wiring them up to create both complex as well as simple workflows. We have out of the box information extraction capabilities, including our partner basis technology and other technologies built into the system, including things like social network analysis and things of that nature. And of course, we have the ability to export everything to search. So you can create a very simple pipeline that simply says, take my documents on HDFS, index them, and then I'm done. Or you can make something much more complex where you say, take my documents, take some seeds that are on HDFS, crawl an external resource, bring those in as a sequence file on HDFS, iterate over all of those, generating additional metadata that's then stamped back onto them, and then forward that on for indexing. And you can also directly from within this environment, you can monitor your workflows as they flow through the system, and then you can analyze the data in different ways. I mentioned mad cow disease before. This is mad cow disease in a nutshell for any biologist in the audience. This is it. I'm not supposed to run away from the light. I've got to go back to the light, but the prion protein disorder right there, or prion protein, and human prion protein, prion sometimes said too, but the ability also to do, to take that same data that's on HDFS and to visualize it essentially in different ways. So this is all metadata that's been generated out of the big data resources using these various extractors. And we haven't even gotten to indexing that data yet, but we're able to interact with it to project the locations that we've extracted directly onto various geospatial resources to be able to look at that data. And you can see this is coming directly off of HDFS to be able to do it. But once we're ready to index it and we want to index it, how do we say, what is a protein name and how does it get indexed in terms of the schema? And so this is where we integrated via the LucidWorks REST API. So we have the ability now to create new collections and to create schema fields and assign them in different ways to different properties to be able to create your search experience. And then once you're done with that and all of that data has been indexed, the question is how do you create a compelling search environment? And so once again, we turn to the integration of the LucidWorks API where we can now interrogate the schema from the search experience itself. So this is the ZettaSearch Designer. This is designed for end users to be able to search across data, and they can search across that data in a very Ajax-y sort of way using drag and drop. And you can even do, here's something you can do here. You can create your own, I think this works. Oh, I thought I had a lighthouse in there. I'll find out in a minute. You can create your own search experience and assign through the API then to particular pieces of metadata that have been generated. So here we have for our search on Japan, we can see we got 1,369 results back for it. We can look at those individually, but we also have here all of the top 10 locations that were also indexed out of that data. And using through the API, we can then say, well, I really wanted to look at the top 10 people that were mentioned within that. William Pesek and Nick Gentle and Brent within that same data. And we can do that with any one of these particular analytic tools, bind them to the particular data that's critical for me to be able to get my job done. And you can do that using both traditional faceted capabilities and drill down on your data. So now we have a subquery. We took Japan and we did a subquery of Toyota, and it updates that in real time to be able to update that search experience. So that is the capability in a nutshell. And I had a placeholder here for the demo. I did want to just summarize that since I think I'm nearing the end of my useful life. So in summary, big data search and analytics has many challenges. There's the volume problem, the variety problem, the velocity problem. And the difficulty associated with the intelligence necessary to extract structure from unstructured information. Hadoop processing enables each of these aspects, especially helping with the volume and the variety, and in turn actually helping with the velocity as well. It's not a real-time system. These are indexing pipelines that work in typically a batch sort of mode, but it's a faster batch mode. And so controlling indexing and search is enabled then for our solution both on the indexing side by helping manage collections and schema, and then on the search side by being able to, in real time, interrogate the search from the end user's perspective. And that's all through the Lucid Imagination Search API. And so we can enable complex user interactions with big data on a really a self-serve basis, so that the end user now within an enterprise can create exactly the search experience that meets their particular needs. We talk about these kind of mythical analysts, where the analyst on the financial services floor in this cube is interested in oil production rates in Central Asia. The guy 2 cubes down from him is interested in commodity prices in Central America. And people like that who need to be able to get at data in different ways, and you don't have enough IT people to meet all their needs. And I think I'm about out of time. Am I out of time? I have 5 minutes. Okay, so I'll just show you a little bit of architecture for those of you who are technically inclined, and then we can have some questions. This is in terms of the authoring environment. Starting on the left, we have a rich internet application. It's written in Flex, which infuriated me when Apple didn't support Flex, but that's another story. I will not speak ill of the dead. It controls an application server through XML and JSON orthogonally. It can also have access to a GPU cloud to be able to do GPU cloud-like activities. And it, in turn, is then controlling the Hadoop cluster to be able to operate these indexing and information extraction pipelines. A lot of what we do under the covers, then, is things like named entity extraction, intelligent named entity extraction based on a variety of different approaches, including supporting commercial partners to do that. And then the information that's extracted, as well as the original data, gets indexed into a Solr cluster, LucidWorks Enterprise, and that then can be searched. We also have connectivity to business intelligence tools. We have a partnership with a company called Quantum 4D, and you can also use Tableau and business objects and things like that. And so in that case, what we're doing is we're materializing views out of the big data resources, and we're using an RDBMS as an intermediary to do that, because these tools traditionally bind to that. From the, in terms of the search, just to emphasize the topic of today, and that is the LucidWorks API. After we push the material into there, some of the different capabilities that this API provides are the ability to get information about individual collections, to create new collections, to create fields within the schema, to delete fields, and to edit the fields in the different types. And so we have all those capabilities directly from within it. And with that, I will open it up to questions.
What do you use for crawling? Do you have your custom crawler, or do you use Nutch or LucidWorks crawling?
Yeah, so Nutch was a bit of a problem because of the Hadoop version was lagging behind it, which is ironic in a way because, of course, Hadoop was originally part of Nutch. But we support Nutch, but it has to be on a separate cluster. And so we created our own crawler technology, and you can also use the LucidWorks crawler to crawl into the collections. Okay, thank you.